Hi, welcome back to the breadboard. It is June the 4th, Saturday, and that means that it is time for the final episode of our Texas Instruments IoT week, where we've been building up an IoT node, which, if that'll focus, where we're monitoring temperature. We have a high and low set point, and we are sending the data we're collecting up to the cloud onto an MQTT server, and we are also reading it back into a Node-RED instance running on a Citara processor with Linux. And we are allowing ourselves to have a smart interface based on an Android phone or anything else that can run an HTML5 browser. So that would include iPhones, desktops, tablets, etc. We're trending our data, little graphs and gauges and all sorts of things like that. We've got switch control, so we can flip between manual, automatic, turn the fan on and off remotely, and change the set points using sliders. All cool stuff. And we've got the local display on here as well. But the last thing that we want to do with our project is we want to get it running from a solar panel. I'm not quite sure whether this one's going to be big enough. And use a LiPo battery. Here's one that is 3.7 volts at 1200 milliampere hours. So this should be sufficient between this and this to power the node that we're using, but we're going to have to measure some parameters to see what we're actually currently consuming on our IoT node. Hopefully it's not too high. And the other thing I'm going to use is a little booster pack, which was developed in collaboration with Element 14 and Texas Instruments. It's now obsolete, but I'm using this platform because the chips that are used on it are not obsolete. There are a couple of buck boost converters on here, and I'll provide all the links and everything else to you, that will convert the battery voltage from 3.7, up to the 3.3, or down to the 3.3 and up to the 5 that the board or any other board may require. It also has a gas gauge on it and a LiPo charger. Now I'm going to have to make some slight modifications for this because the pinouts on here conflict with some of the pins that are being used by the Samsung display, etc. Most of them I don't actually use anyway, so all I'm going to do is remove some 0 ohm resistors to isolate it. The two key ones, and if we get time we'll look at this, for the I2C bus though, this board was designed for an MSP430G board, where the I2C bus is actually on the other side of the board on pins, I think, 14 and 15, instead of on 9 and 10. And all the new launch pads and things like that all use pin 9 and 10 for the default I2C bus. So this, of course, will not, we won't be able to talk to the gas gauge without some heavy modifications. If I get a chance to modify it so that we can, I will do that. But at minimum, I want to at least get this acting as the charge controller. It will take anything from USB power, so just to 4 or 5 volts from USB, and you can also plug in solar power. So what I'm hoping to do is use the solar panel to go into this board, charge the LiPo battery, and at the same time run our little IoT node based on the CC3200. So the first thing we need to do is let's verify that, one, the solar panel will give us the voltage that we want. Two, we need to modify the board so that it's not going to mess with some of the other pins. And I'll show you a spreadsheet here which has all the mappings of the pins as they are right now. And then you'll understand why I need to break a few of the traces from this little battery booster pack from that I have. The last thing we will have to do, of course, is then hook it all up and see if it all works. Now, in the process, we're going to measure the current drawn by the Launchpad in its current configuration. So we're going to stick it onto one of my multimeters and see what it's drawing from the USB bus. As I said, hopefully it won't be much, but we need to be sure. So let's get to the bench, and the first thing we'll do is measure the power consumption of the current configuration. Okay, what I've done is I've hooked up a USB power supply here through a little breakout board that I made for a couple of years ago for a project that I was doing. And what this has on the back of it is a 0.01 ohm resistor in series with the positive supply rail. What that does is allow me to measure the current going into a device without having any nominal effect that's significant on the voltage being applied to the device. If I use, say, a 1 ohm resistor or something like that, I would be dropping a reasonable amount of volts across the sensing resistor, thereby impacting how much current the system would be drawing, because the volts being applied to it would also be less. By using a 10 milliohm resistor, I'm only dropping, in this case, 470 microvolts across the load resistor for the load we're taking. And if you do the math on that, it means that we're drawing around about 50 milliamps of current to power this. Now that's what this meter is doing as an average perspective on here. If I show you that right now, you'll see it's all right, it's got 483, but it's also showing on an AC with DC about 480 millivolts as well. So what I really want to do, just in case this is not reading correctly, is I'm going to try it on my Keysight 7.5 digit multimeter. The reason for that is because it has a graphical display that should be able to show us any spikes and maybe figure out what the actual average current is rather than what my U1461 is reading. It may end up being the same, but let's go have a look. So the first thing I'm going to do with the Keysight 34470A is to measure the actual value of the resistor. So you can see here, even though I thought it was about 10 milliohms, it's actually near 11 milliohms. So I'm using 4-terminal measurement to improve the accuracy. So now we know that we're actually going to be reading slightly higher millivolts than I thought. So that's one thing done. Now I'm going to convert back to voltage measurement, and we'll power up the unit again and see what voltage we get. So after initial power up, you can see here that we're getting about the same 470 microvolt reading as far as an average reading is concerned. So let's just do the math. Now we know it's on 11 milliohm. So that brought the current down to about 42 milliamps. Now we want to be able to see if this is spiking, and and maybe the average is actually a lot lower and it's just being skewed a little bit. So let's flip to a graphical display. So this is going to capture the data of the unit running for a period of 5 minutes. So let me come back in a couple of minutes and I'll update you with what we're seeing. Okay, we're 3 minutes in now of our 5-minute run, and what you can see here now is that here's 400 microvolts, which means that this is 600, so we're still sitting with an average of about 47 milliamps. So divide this by 10 basically, because of the 10 milliohm resistor. And you can see there's a lot of spikes here that are actually going up to around 700 microvolts, which means around about 60, 70 milliamps. Now 700, let's go to statistics rather than me trying to guess what these are. This meter, the 34470A, has the ability to show statistics on these readings. So let me bring them up. So now we can see the minimum voltage that it's reading is 460 millivolts. Its average is 490 millivolts, and a peak of 71. So if we do the math on the average 49, so 0.00049 divided by 0.01 ohms equals, 0.011 ohms, that's 44 milliamps, just over, that we're consuming as an average. But as a maximum, we've got 710 microvolts, which means 0.00717 divided by 0.011 equals, we're actually peaking at about 65 milliamps. Now from a battery perspective, the average is probably what matters, even though we've got little peaks. So if we base it on about the fact that we're going to need around 50 milliamps of continuous current being supplied to this. That's what we need at the 5 volts. So now let's go and have a look at what we can get out of our solar panel. So here's the booster pack. I've connected the battery, and what I've done is I've taken an older USB cable and I've just cut the end off of it so that I can make the solar panel connections. So I'm going to do that now. Before we go outside, it's certainly not going to get enough voltage on this booster circuit to charge the battery inside on a flashlight or the interior lighting. So let's modify this board so that I can plug it into our IoT stack, and then we'll go outside and see what it will do. As a close-up of what I need to modify is the board close-up. There are 3 resistors here, tiny ones, this one, and this one. They need to be disconnected. I'm just going to unsolder them. And then there are 2 tracks here that are running out to the MSP430G type booster pack Launchpad connections for the I2C. So what I'm going to do is I'm just going to cut the pins on this side of the board so that they don't even plug in, rather than hack this, and then we'll go from there. So quick word of warning, I was just making up a lead so that I can actually drive the booster pack with a solar panel. And what I did was I took a standard lead that I had laying around, I just cut the cable off, stripped them back, and I got red and black, which are the traditional power wires for for low voltage DC universally, where red is normally positive and black is normally negative. And this was the cable that I used here. There's the red and black stripped. It's a little bit thin, but I was only using, a few hundred milliamps at best to try. This cable is made up with the black being positive and the red being negative. Unbelievable. So I grabbed another one thinking maybe I got something wrong, and here it is. This is a slightly heavier gauge one, a little more expensive, but here it actually is red positive, black negative. And I know that there are some universal standards for the color coding for USB cables. You've got the red, the black, the green, and the white. And the green and the white are the data cables, and the red and black are the power cables. And you can see here that the charging light is now on here. So it's charging this battery. Now I'm running it from a power supply right now because I wanted to crank the volts up to about 12 or 14 volts to see what would happen. But when I hooked this up originally with the other cable, I had the current limit on my power supply set slightly high. And IC1, which is the LiPo charging chip, sorry, IC2 right here. Right there, if you can focus, I'm not sure. Anyway, I'll show you the schematics about now, and you can have a look for yourself right here. Anyway, IC2 got red hot, and what it was is probably got a diode inside for reverse current protection, or the FETs or whatever started conducting backwards, and it got really, really hot. Now, right now, it seems to still be working okay, but I'm not going to hold my breath. I might have to ditch this board if it doesn't work out and use another one. I'm just going to test a couple of the output voltages to make sure that they are still giving me what I expect. What I should be able to get on here, if I'm just going to connect to a ground on one side, just here, right, and I got my U1272 here. Fortunately, I had disconnected my the rest of the circuitry from it while I was playing with this. So I didn't damage anything, and not that I necessarily would have done, but had I had everything else plugged in, who knows what I could have done. Anyway, so here we go. I should get 3.3 volts here. So I still do get the right volts coming out. And I should get 5 volts on this side. And I still do. Now let me just disconnect the power charging. Shouldn't make any difference. The light's gone off. So at least part of the chip is still working properly. And still got the 3.3 as well with it on battery power. Yep. So plug that back in, it's on charging. So at least that's good. And if I check the input voltage for charging right now, you can see it's sitting at about 5 volts. I'm going to slowly increase. One of the things that I wasn't sure about, the chip's supposed to take up to 20 volts. My solar panel is going to output about 12 or 14. If this one I've got, which is a 5 volt one, doesn't work out, the one I'm going to use will output about 12 or 14. It now explains why this one didn't bring the charge light on too, of course, because it was reverse connected. So it's just a short. So I'm going to up the voltage to no more than about 14 volts. It should be fine. There is a cap on the input, and I can't find out what voltage rating it is. I'm hoping it's going to be about 16 volts or more. So the current's just cut off there. So as soon as I'm hitting to 8 volts on the input, it's no longer going to be charging. So that's what I thought. The chip, it's probably the configuration of the chip that's to do with charging. I'm not sure. Let me just grab a different one just in case this one got fried. Okay, so this is another one. Charge light is on. I've got 7 volts coming in right now. You can see the charge light just here, I think. Anyway, let me just increase it and see if it also, yeah, that also turns off. So there must be a threshold set that at 7 or 8 volts, at 9 volts, it's going to cut off. 7 volts is fine, 8 volts it cuts off. So I'm not going to be able to put a 12 volt charging solar cell on here because it's not going to work. But now that I know that the wires were incorrect, I should be able to stick the solar panel back on here and see if even with a flashlight I can get some volts out of it, enough to get the charge working. So let me just get the solar panels again in parallel. Hopefully this time they're going to start the charge light up. So I'm just going to put this back to the one I was playing with. And right now I'm just twisting these wires together just for experimentation, so please forgive that. Okay, right now we've got about 3.5 volts on the solar panel, and the charge light is not coming on. Now this will be running on battery at the moment because that's what it's designed to do. So we should have still 3.3 volts and 5 volts. Yep. So now let's get my flashlight and see if, yeah, 3.47. That's now up to 4.2 volts, and the charge light has actually come on because that's enough to charge the battery. Now whether it's being able to provide enough current is another thing, but out in the sun it probably will. So next stage, get it all hooked together and let's get out in the sun. Okay, so what I have set up here right now is these 2 small solar panels over here. I've got 2 meters, one measuring the current in milliamps and one measuring the output volts. Now we're right outside in the sun, so it's getting a little bit difficult to see this one on the left, but it says it's outputting 4.2 volts right now and 31 milliamps, and the 2 solar panels over there are in direct sunlight. Now we know that the solar panels are not going to give us out more than about 50 milliamps, and that was with a short circuit. Now I've got them in parallel and it's only giving out 4.2 at 30 milliamps. So based on the fact that we know that this system takes about 47 on average while it's running, that's not going to be able to sustain it. So what I have is I've got a bigger solar panel here, but it's 12 volts. It is not 4.2, it's not a 5 volt cell. So of course if I put this on here directly, it's not going to work because it's not going to like the amount of volts that are coming out of it. It's just going to shut it down. So what I have is a little buck converter which should efficiently convert the 12 volts down to 5 volts, which we could use for charging. So I'm just going to wire that up and we will see what we get. So this panel I'm just going to stick in the sun and we'll see what kind of volts we get off of it for the moment. As I say, it should be about 12 volts. Let me just take this meter and put it on here. So that in the sun right now is giving us open circuit 20 volts open circuit. Now let me see what current we can get out of it. Now I'm gonna have to switch meters because this meter will it's only got a milliamp range on it, not an amp range, and I don't want to blow the expensive fuses in there. So let me just rearrange these. So it seems to be only giving out about 70-80 milliamps. It is only a small cell, and that of course is short circuit current as well. There might be a chip in there to protect it. See what the box says. Solar, 12 volt battery, charge batteries, blah blah blah. What wattage? 5-year warranty. 1.8 watts, which means at 12 volts that should be able to give out 125 milliamps. when it's running at full sun at 15 volts. So that's going to be more than enough for what we need, but of course the voltage is wrong, and because of that, when we put it through the buck boost converter, it's actually going to give us more volts, more current than we need as well anyway. So let's just hook this thing up and we'll see how it works. Be right back. Okay, let's just make sure first of all I've got this unit hooked up to the solar panel. Let's make sure we're getting the right volts out to start with. So if you can't, I'm going to read the meter volts out anyway. So it's outputting 5.3 volts right now. Let me just tweak that a little bit, see if I can improve that closer to 5. Alright, 5.07, that's close enough. So that now we should be able to wire that into our charge circuitry of the booster pack battery power and keep going. Okay, so the sun is starting to fade a little, but nevertheless, looking at the voltages I've got, I'm pumping 620 milliamps in with a slightly faded sun into the solar panel, into the battery booster circuit. I've got, because the sun's low a little bit, the volts has dropped to about 4.1 volts. I don't know if I can tweak that at all. Yeah, so we've got enough that looking at the back of the unit, the charge light is definitely on. This is taking on average about 47 milliamps, so we've got 61 going in. If I try and adjust the solar panel a little bit, I might be able to get that increased. Let me just go and have a see if I can. So I'm getting up to about 70 milliamps of volts going in. So it's certainly enough to be able to charge the solar panel. And you know, so if that's pumping in all day, maybe a slightly bigger solar panel, but I think it should be sufficient in decent light. Yeah, so the solar panel right now is not able to pump out enough current, even allowing for the fact that we're going through a buck boost regulator, a buck regulator. It's still not quite enough. I think if I was in the full daytime sun, it would be. Now, obviously, the ideal would be to put a slightly bigger solar panel on there for charging this, or somehow reduce the consumption of this. Right now, with 47 milliamps, 8 hours of charging would not give you 16 hours of operation. It certainly would extend the life of the system, and I think you'll agree that this kind of is proving that the overall system does work. It's just we need slightly bigger solar panel. I don't have one available right now. Oh, maybe I do. I'll be right back. I might have one. Okay, so now I'm going to be slightly overpowered because I don't have one in between the one I just showed you and this one. So as you can see, that's a little bit overkill, but it should do the job. The little one there without full sunshine is not going to give me enough current to do what I need, so I'm going to use the bigger one just to finish the project off with, just to show that it will work. So I'm not sure how well you can see the displays at the moment. I think I'm slightly out of range of the Wi-Fi where I am as well, trying to catch the sun. But nevertheless, let's plug this in. Oh, that's going to work. Okay. Which, did we really have any doubts that it would work? I don't think so. So we now have 420 milliamps going into the charge circuit. We've got a full 5.2 volts coming out. So I can even tweak that down if I wanted to, not that it's necessary. Charge light's fully on, system is running. So with 400 milliamps going in and 5 volts, we're going to easily charge this up and keep it going. My point here, I think, is that as a solar-powered system, the chips that we use on the buck boost regulators, the battery booster pack, are certainly capable of doing the job. The lithium charging system, actually, the way things have worked out, it's shown itself to be pretty resilient as well. Will certainly drive enough power into the battery pack to charge it in a matter of a couple of hours. In fact, with the bigger, obviously with the bigger panel, it's going to work better. And the system, the biggest concern you have of bringing it out to the sunshine is keeping it, of course, in range of your Wi-Fi. Right now I'm out of range, which means my updates have stopped because it's trying to reconnect to the Wi-Fi system, and that's not going to work. If I go very close to the house, it will work again, but then I'm in complete shade from the sun. So I just wanted to bring it out here to show that the solar powering of this would work, and that these battery booster boards will do the job. I had to modify it, as you remember, but the chips that are used for it are perfectly adequate and will supply a number of different things. So let's go back in, we'll bring up the schematics of the booster board, and I'll show you a few things that make this a very useful set of chips for any project pretty much, never mind this one. Anyway, the sun's about to disappear completely in a minute, and so I'm going to wrap up this outside, and we'll go back to the PC, have a look on the computer, and we will review everything that we've done up to now. See you back inside. Now, just before I go back inside, I've just unplugged the booster pack from the main module just to see, and I did some calculations based on the component values that were on the board, and I estimated that it would be drawing about 250 milliamps to charge the board, and that actually is now borne out by the fact that the only thing connected is the booster pack itself with a cell on it, and it is indeed pulling 250 milliamps from the solar panels. The rest of the current would have been getting pulled from the CC3200 and accessories that are on there. Now, one of the reasons why it was probably also going up over 100 milliamps is the Wi-Fi was disconnected, and it was probably cranking the settings up to try and re-establish, and spending a lot of time sitting there on the Wi-Fi transmitter and receiver trying to get some connectivity going. So that would explain why we had a bit more than 250 milliamp when we were up to over 400. So that's as good a reason as I can think of anyway. Now back to inside. So through this whole today's video, we've been looking at or predominantly focusing on the fuel tank booster pack from Texas Instruments and Element 14. Now, what is on this board is quite interesting, more than the fact of the board itself. The board actually is obsolete, so you can't buy one now even if you wanted to. But the three different chip types that are on here, well, there's two variations of one and two other ones, are still currently available, and so can be incorporated into any designs of your own. Now, the first and key one here, of course, is the BQ24210 LiPo charger, and in our configuration, based on a couple of resistor values, it is charging the 1.2 ampere hour 3.7 volt lithium ion battery at 250 milliamps, but you could easily increase that if you wanted to. Now, of course, the consumption, if you're running off of the battery booster pack, is that you have to provide enough current to charge the battery and enough current to charge your launch pad. If all you're doing is providing enough current for the launch pad itself and accessories that may be connected to it, then there isn't enough left to charge the battery. So you need to account for the fact that you want 250 milliamps for the battery based on the schematics of this board, plus whatever you're consuming for your application. In our case, this was about, let's just say, 50 milliamps average and about 70 plus milliamps peak when the transmitter is working. So that means you need in excess of about 350 milliamps available from whatever you're plugging into this USB charging port. We've seen already that if you go above 8 volts on this input, it will shut down. That's also based on the LiPo charger thresholds and the way that it operates to minimize the power dissipation, etc. As you can see here, there are absolutely no heat sinks or anything, and these chips are tiny. I've already done some rework on a previous board way back on another video that I did about probably 2 years ago now, where I had to replace one of these buck boost regulators. But anyway, that's another story. So you've got the LiPo charger is the key to this. Now, one of the other points that we have in here is this BQ27510G3 gas gauge. This is connected to, in this particular board's case, the legacy I2C interfaces that were based on the MSP430G series of launchpads. Now the pins down here are used for I2C. So I cut the tracks around here on this board so that I could plug it into my stack and not have it interfere with other GPIO pins. Plus, these three resistors were also removed because they were conflicting with the SPI LCD display that we were using. So and they provide enable power good and charge indicators into the microcontroller. So as far as just providing power, it's not essential that we had them. And I wanted to show you this working with solar and a LiPo, and to demonstrate the fact that you could make this standalone from solar alone with a battery backup for nighttime use. These two chips here are the buck boost converters, and what they do is one of them is a pre-program for 3.3 volts and the other one is for 5 volts. Now in our case we actually aren't using anything that is 5 volt enabled, so if you were building a power board of your own, you wouldn't need to have both of these buck boost converters on. You would just need the 3.3 volt one. And this whole board actually doesn't consume much power at all when it's operating. Obviously it's taking power for charging the battery, but the quiescent current for the chips is very, very minimal. And if you look at the data sheet for the LiPo charger, you'll see what I'm talking about, although I will point to those two resistors in just a moment. This is one of the modifications I did to this when I first reviewed this board probably a couple of years ago now. So going down here, let's just go to the schematics of the board, because that's really the next thing that matters to us. All right, so what we've got on the board is we've got two buck boost regulators. Here's the first one, TPS63001, provides us 3.3 volts into the launch pad. And the other one is a TPS63002, providing us 5 volts into the launch pad. Now both of these buck boost converters are able to actually deliver over an amp each. So they are very, very efficient, and considering the fact that they're only, I think, about 3 millimeters by 3 millimeters on the board, they work very, very well. And I will provide a link to a road test that I did with these, like a review, quite a while back. There were some modifications I did to the board to improve its operation, and it was based around this R19, R20, and the R17, R18. In the configuration that they have, which is where R18 and R20 is populated, the buck boost regulators are actually consuming a fair amount of quiescent current because they're keeping an active current through the inductor irrespective of the output voltage. By moving the resistor here to the R17 and R19 position, you put it into a low power mode where it minimizes how much current is put through here, providing the output to the feedback is giving the correct voltage. So it significantly improved the standby capabilities of this booster pack from a matter of a day or two to probably in excess of a couple of weeks. The gas gauge is basically a standalone chip where its main purpose is effectively it's monitoring the current coming from the battery pack to ground. So it's got a 10 milliohm resistor in here, and it monitors the current going through and the voltage, and actually gives you an estimation of the capacity in milliampere hours, how much time is left, and a whole bunch of other really, really cool statistics of the performance of the battery. So with an I2C interface, you could interrogate this and find out that you've got 50% of power left, or 100% or 80%, whatever it might be. Know how long it might take before the battery is full charged, at the current charging rate, and a whole bunch of other useful information that you could provide to a user or a system that's controlling this. In the case of today's video, though, we're not using the gas gauge. I've effectively cut it out of the circuit because I disconnected the I2C and didn't connect it to the new pins and set up the software for our little stack. I will actually circle back on this in a future video and show you how you can use the gas gauge, as well as maybe do some tweaks on the LiPo charger to increase the charging current, because in some circumstances, if you have a bigger battery or a shorter sun period, then you probably want to get as much current into the battery as you can while you can. The other three resistors that were disconnected, which I showed you just a minute ago, was the R11, 12, and 13. Now these are the charge, the enable, and the power good lines that come from the LiPo charger, for one, where's this charge indicator. It actually goes from charge to charge LP through the serial resistor. You got your power good, your enable, and your charge are all on here. So these were disconnected to prevent them from interfering with the pins that were being used by the LCD display. The only thing that I would change on here is that currently when the gas gauge decides that you have a battery low condition, it puts an LED on to tell you that the battery's low, but then it instantly kills the buck boost regulators by sending a battery low to the enable pin on them, which shuts them down. So that's just because of the implementation of this board. It's not a problem with the buck boost regulators or the gas gauge or the LiPo charger, which are all TI chips and are all very, very good for the purpose that they are designed for. I would just not have the low power indicator connected to an LED, and certainly not connected to the buck boost regulators, so that you get that extra bit of time to shut down gracefully, perhaps under programmatic control. So I think that about concludes our last day of the CC3200 Texas Instruments IoT week. We've now successfully put our node onto a solar panel with a LiPo battery backup so that it can run day and night, even outside and disconnected from the rest of the world, except for the Wi-Fi connection, of course, providing it's close enough. And happily work that way. So I think the week has gone very, very well. I'm quite happy with the results. And I think I've provided you a lot of information that you can take away and play with and experiment on your own. If you have any questions, please feel free to send me an email, post a comment in the comments for the YouTube videos, or of course you're quite welcome to go and ask TI directly. So if you liked it, please give me a thumbs up. If you didn't, well, then you don't have to. But I will be producing a lot more videos for the Texas Instruments chips, Arduino chips, Raspberry Pis, etc., and probably the BeagleBone Blacks are going to be added to the mix as well really, really soon. And I hope you will follow along and subscribe to my channel so that you can get notified of any new videos that I put out. In the meantime, have fun, be safe, and I will see you on the next video.